So day 2 of these 9.3 notes start off talking about the harmonic series. Now, the harmonic series is something that Pythagoras and his students kind of looked at, paid attention to, and as they were studying music. I don't have enough background knowledge on this to really dive deep into it. But if the history of math interests you, which was a fun class that I got to take in college, there's plenty on YouTube about this. There's also we should watch Donald Duck in Math Magic Land. They briefly talk about this. Anyway, the harmonic series is one that I've referenced in a couple of problems. It's the series from 1 to infinity of 1 over n. And we have been saying that this diverges. Its terms would be like 1 plus 1/2 plus 1/3 plus 1/4 plus ... 1 over n, and it would just keep continuing on. 1 over n plus 1, 1 over n plus 2, etc. Now that's just one specific harmonic series. A general harmonic series could have a constant in front of n, and it could have a constant added or subtracted from n. And so here's the only thing I understand as far as like with music. This kind of makes sense to me, this part right here. I know nothing about reading music, musical notes. I can't play any musical instruments. It's something I regret not learning as I was growing up. So anyway, it does make sense to me, however, that in music, if you had a stringed instrument and all of the strings were the same material, diameter, tension, it makes sense to me that the lengths of those strings, if their ratios came out to form a harmonic series of some sort, either this one or a more complicated one, then it might produce some nice sounding tones. I did link a video if you're interested in learning more. I haven't watched the whole video, which is why I'm still so lacking in my knowledge here. But this guy seems to know what he's talking about. He seems pretty excited about the harmonic series, and it's like a 15-minute video. So, I will work through this. But again, I can already tell, beyond anything I know. But for those of you who are in maybe music theory or just interested, feel free to check that out. Anyway. Okay, what do we do with this in calculus? What do we need to know? First thing we need to know, the harmonic series diverges. That's something that you just kind of want to have memorized to begin with. So that's something to store away into your brain, but I am going to show you why. Why does it diverge? Well, yesterday we were talking about the integral test, right? So let's take this 1 over n, and we'll come up with an f of x that's equivalent to it. 1 over x. It's equivalent at all the integer values. And 1 over x is in fact positive, decreasing, and continuous on the interval 1 to infinity. So I can go ahead and say, well, let's just figure out what the integral from 1 to infinity of 1 over x dx is. And then we can determine whether or not the actual series converges or diverges. Now remember, the long way to do this is to come up with like, oh, this is natural log x from b to 1 and limits and whatever. But also, remember in chapter 8, we called this a p integral. I was doing that to set you up for the idea of p series. There's not really officially a thing as a p integral, but there is such a thing as a p series. So remember, if the power on that x is less than or equal to 1, then we know that that integral diverges. It doesn't decrease fast enough for the terms to stop adding up and growing. Okay, so since this integral diverges, it means that the series diverges as well. So the harmonic series is a special p series. So p series are in this form. P series has to look like the sum from, let's say, 1 to infinity of 1 over n to the p. The harmonic series is when p equals 1. But you could have 1 over n squared, 1 over n to the third, whatever. And so these terms are going to be like 1 over 1 plus 1 over well, 1 over 1 to the p technically, plus 1 over 2 to the p, plus 1 over 3 to the p, plus dot, 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 1 over n to the p, etc. And just like for p integrals, the same rules apply for, well, not the same rules, similar rules apply for convergence and divergence. So again, harmonic series is when p equals 1. But the p-series test is just telling us, all right, if you've got a p-series, so it's in this form, as long as p is greater than 1, oh, this is our same rule, sorry. As long as p is greater than 1, then our series is going to converge, which was the same rule that we said for integrals. Now, we don't know what it converges to. We just know it converges. And this series will diverge if p is something between 0 and less than or equal to 1. If you don't have this equal to written in here, make sure you write that in. Okay, so remember, for p integrals, we could figure out converge, and we could say, oh, converges to 1 over 1 minus p. But p series, we can only say converge or diverge. We cannot say what it converges to. Remember the idea that, like, hey, the area under that curve is not going to be the same as the area of just finite points on the curve added up. There's no way. All right, so let's look at some example problems here. This rule is only if you have a pure p series, so 1 over n to the p. Anything that's similar but maybe has extra terms or something like that can be looked at with a direct comparison test, which we also did in chapter 8, so that's coming back to us. So for example, something that's similar would be like the sum from 1 to infinity of, instead of just like 1 over n squared, maybe it's 1 over n squared plus 1. We'll be able to compare that to the 1 over n squared p series and figure out how it relates. All right, before we move on to these, let's make sure we know the difference between a p series and a geometric series, because it's easy to kind of mix them up. First of all, know what they look like. So the integral from 1 to infinity of 1 over n to the p, that's a p series. So the number that you're plugging into is the base. A geometric series is the sum from 1 to infinity of some a times some r raised to the n power, where the variable that you're plugging into is the exponent. All right, and again, our rules for a p series, if p is greater than 1, the series converges. If p is between 0 and 1, series diverges. For geometric, if r is between, excuse me, is between 0 and 1, we say absolute value because r can be positive or negative. If it's between 0 and 1, not including 1, then the geometric series converges. And we can say that it converges to whatever that first term is over 1 minus r. Actually, I don't want to write a sub 0. I just want to write a. But remember, that's like first term. Could be a sub 1, a sub 0, a sub 5, wherever they start. If r, absolute value of r, is greater than or equal to 1, then diverges. So we can find the sum of a geometric series. We cannot find the sum of a p series. So discuss convergence or divergence. All right, so first of all, this is a p series, right? P is equal to 2. That's bigger than 1. So all I have to say with this is that this converges by the p series test. So this is a case where, sure, I could do this with the integral test, which is what all the space down here is for, but I don't want to do it with the integral test. If I already know that I could do p series, remember, integral test is the last thing you want to try. So moving on to b. 1 over 2 to the n. Remember, that can be written as 1/2 to the n power. This is geometric. r is equal to 1/2. A sub 1 is, because that's where it starts, A sub 1 is equal to 1/2. So this converges, and I know it converges to 1/2 over 1 minus 1/2. 1/2 over 1 minus 1/2 is equal to 1, right? So this converges to 1 by the geometric series test. What about C? 1 over, now this might as well be 1 over n to the 2/3, right? That's a P series, but P is equal to 2/3, which is less than or equal to 1, right? And so that means that this series diverges by the P series test. So we hope to get a bunch of P series and geometric series on the AP test. That'd be awesome. Oh, what if you're just given the terms? You have to come up with the formula here. So you can either come up with the formula just by kind of looking at it, or some people like to start by dividing terms just to see if it's geometric. But let's see, this looks like 2 to the 3rd, 3 to the 3rd, 4 to the 3rd, 5 to the 3rd. So this looks to me like if I started at 1, which is just what I picked, you could start at something else. But anyway, n equals 1 to infinity. It looks like it's 1 over n, not, let's see, it was always to the 3rd, right? N to the 3rd power. Okay, so that is a P series where P is equal to 3, which is greater than 1. So this series converges by the P series test. I don't know what it converges to. That's not what the P series test tells us. All right, what about this one? Let's see. 2 over 3n plus 5. Now, we have not officially learned in this chapter about direct comparison test. So that is something that we're going to use in a minute. But this is not geometric. This is not P series. So my last resort at this point is to use the integral test. I can come up with a similar f of x, 2 over 3x plus 5. From 1 to infinity, that is positive, decreasing because it's bottom heavy, continuous because negative 5/3 is the vertical asymptote. So I can say, all right, let's do the limit as b approaches infinity of the integral, sorry, from 1 to b of 2 over 3x plus 5 dx. This is a little u sub. U is 3x plus 5. Du is 3 dx. I have 2 dx. I'm not, you can't just like add 1 or anything. So if I need a 3 in here, I'm going to put a 1/3 out here. Or you could pull the 2 out and say, all right, actually, I think I might do that. And say, now we've got the limit as b approaches infinity of, so I'm going to pull that constant out along with my 1/3, 2/3. The integral from 1 to b of 1 over u du. That way I don't have that extra 2 on top, not that it's a big deal. All right, so let's integrate. We get 2/3 times the natural log of, what was u? U was 3x plus 5 from 1 to b. That's the limit as b approaches infinity of 2/3 times the natural log of 3b plus 5 minus 2/3 times the natural log of 3 plus 5, 8. The natural log of infinity is infinity. And it doesn't matter that we get this constant. So this series diverges by the integral test. All right. So that's it for today's notes. And we will come back together on Friday just to do a review. So today was the last day of new information. If you haven't done assignment number 14 yet, now you should be able to do it. I'm scrolling through it to see. I think it was all integral test. Yeah, so you could have done it last night because there aren't really very many P series, if any. I think I saw one contender. All right, that's it for today.